Good morning, everyone. Thank you very much for attending my presentation on the development of a modular sensor suite for propulsion testing. Uh, the company is called Energa Incorporated, and it means environmentally friendly use of energy. We'd like to thank NASA for this SPR grant that made this work possible with Glenn Gusick as the program manager. I have four other co-authors with me, who is John McClim, Marcus Wolverton, Vinod Narayan, and Jason Green. Hopefully they are listening to this on the other streaming site. The first slide I have up is the background and motivation, which shows the outline of the talk. The first is the background and motivation for this particular project. After that, I'll describe the hardware and software we developed during this project, and finally close out with some results from some demonstration experiments that we did. So, excuse me?
Excuse me, sir. I am the first presenter, sir. My name is Khalid Nanahi. Can I connect with you, sir?
Shall I continue?
Yes, please continue.
Okay, so currently there are several planar and non-intrusive methods available to study turbulent reacting as well as non-reacting flows. Some of them are listed here. Basically, you have emission tomography or planar laser-induced fluorescence. You have TD LAS systems and pattern imaging velocimetries, two-color thermometries, and extinction tomography. As you can see, all these are separate methods that are used specifically to obtain some particular information from these turbulent flames as well as turbulent sprays. The biggest disadvantage with these techniques are that each technique requires a specific setup and will provide information only of a few of the properties that you're looking for. So our motivation was to develop a plug-and-play type non-intrusive sensor suite that can be used for measuring a wide variety of properties in turbulent reacting and non-reacting flows. The two things that we kept in mind while developing this one was that the suit should be able to measure path-integrated radiation with either extinction or emission or even scattering in turbulent flows. And two, the algorithm should be able to use whatever is available on the hardware and to provide relevant information from these path-integrated measurements. So these are the two key requirements we had when we went ahead and started developing this. Once we finished making the system, we also wanted to establish validity of the suit. We did some measurements in flames as well as in sprays to compare with published data if possible. In this particular study, we just looked at chemiluminescence, soot volume fractions, and temperatures in flames. And we do have some prior data on drop size distribution as well as patterns in sprays. I might show one slide of that later in the presentation. So first, let me describe briefly the hardware and software that we are using. Okay, this shows the sensor suite platform. The first thing that we decide is to use a platform where we can just put these different components. Here it shows you this particular platform. We used we actually make optical pattinators, and we use that particular system as a platform. That particular platform that you see right here is about 5 feet in diameter, and the inside part is about 4 feet. So you can put your flame or spray inside in this donut hole and be assured that it doesn't affect the flame, or this water and the hot particles don't enter into your instrument. The instrument itself consists of 6 sources and 6 cameras. So these sources is currently being used to measure drop sizes and number density. The total size of the flame that you can use or the spray that you can use is about 175 millimeters. The inner diameter is 1 meter, and it can be increased even greater if you want to have more clearance from flames. Also, the interrogation diameter can be changed if needed, but this is the platform we use for the phase 1 study. What are the basic elements that make up the sensor suite? The first one is, on the left side we have the sending element, and on the right we have the receiving element. The sending element typically are diode lasers with sheet forming lenses, and the middle shows the sensor suite. Typically there are 12 big lenses arranged in a dodecagon pattern, so that you get 6 view angles that you're looking at. And on the receiving side you have imaging lenses, you have array dictators and optical filters. Now we can use either linear or two-dimensional high-speed arrays, visible IR or X-ray, it doesn't matter. In our particular case, we have been using linear visible arrays to just show proof of concept. And sending models, we use fixed wavelength lasers, but of course you can switch that to other items if you need to. This shows you a photograph of the sending module on the left and a photograph of the receiving module on the right. On the sending module, you have the laser. It goes through some folding mirrors so that the package can be kept small, and then it goes to a big lens, sheet-forming lens here. This is a fan beam laser, so this one collimates it into a parallel sheet. And once it goes through the interrogation area, it falls on the receiving module, which first decollimates the lens, and then there's a set of fold mirrors followed by further lenses inside the dictator package, so that you put the image that is formed onto a linear array. Like I mentioned, we use linear visible arrays and fixed wavelength lasers. We measured soot volume fraction, temperatures, OH chemiluminescence, and folding mirrors to reduce path. As far as the deconvolution method goes, I'll be very brief. Basically, the first thing we did is we linearized the radiative transfer equations. The grid that we use is something that has been published in the past. They provide close to equal radial and angular resolution. So if you want, you can increase the radial resolution while sacrificing angular resolutions, or it's an adaptive grid essentially. The main reason we do linearize a radiative transfer equation is that then we can cast these equations as a linear inverse problem with a positivity constraint, since all the physical parameters you are measuring are positive. So this is a type of system called LINPOS, and this is best solved using the MLE method, which is the maximum likelihood estimation method, and convergence can be proven with this particular method, so you don't have to worry about multiple solutions or the other things creeping into your results. As far as the configurable algorithm goes, what we do is we input a species of interest, and it will tell you what are the available wavelengths. So you have to select that particular wavelength and use the appropriate filters or lasers, and then you can query the database and find out the radiation properties of interest. And after you collect the data, you use this radiative database to perform the deconvolution, and it will return the local properties. So that is essentially what it does. So anytime you change any item, you have to go back and say what your input species of interest are. So the current modules that we have in this database is one for soot volume fraction, another one for intensity, a third one for temperature. This temperature is from particulate concentrations. Then we have another one for gas concentrations like CO2, water vapor, and OH. And this shows the equations that are relevant equations. Typically, all these equations are linearized before we put it into the deconvolution solver. We also have previously done something for drop surface areas as well as drop sorter mean diameters. So we can choose any one of these properties that you want to determine, and it tell you what wavelength to use, and you can go ahead and put that particular filter in there and collect data, and it will print out all these particular properties. So now I think what I'll do is I'll go to some of those demonstration experiments that we did. The first demonstration experiment we did is an overfire region. We used a burner that is a 50 millimeter diameter burner. Inside the burner there is a honeycomb. There are 2 layers of stainless steel balls. This is used to just make sure that the flow that comes out is quite laminar. And on the right hand side you'll see this particular picture. You can see that the flame itself, on the bottom of the right hand side you can see the flame that comes from the burner. The flame goes into a small chimney, and the sensor suit itself is shown up here. It's about 2 meters above the flame. The reason we do that is we are looking purely at the overfire region, and data is available at 2 meters at the overfire region. One of the things that is where once we use this particular chimney, the particles as well as the gas species inside are mixed very well. So you actually do not get that much spatial information, but that is okay, because what we are really looking for is something called efficiencies, like soot generation efficiency, or maybe CO generation efficiencies. That is some of the results are shown here. These are the radial profiles of soot volume fractions from an ethylene air flame that was run at 6 different conditions. Similarly, from a propylene air flame, we ran about 5 different conditions, and it shows you the radial profiles of the soot volume fraction. So this sort of radial profiles are not not available in the literature, but what is available in the literature is soot generation efficiencies. That shows you as a function of mixture fraction what the soot volume fraction is. So from the flow rate of the fuel as well as the flow rate of air that goes into there, we can calculate what the mixture fraction for this particular location output is. And here it shows the mixture fraction as a function of soot volume fraction, which is also the soot generation efficiencies. And you'll see that the present experiments fall almost on top of the previous experiments that we did in 1990 using intrusive probes. The same was also available in propylene air flames. So basically for these overfire experiments, we have very good agreement with literature values. The second set of experiments looked at the underfire region of these flames, and here it shows you the flame. It is right in the middle, and we are looking at a location that is probably about 100 millimeters above the burner. So it is quite bright up there, and we looked at 2 wavelength data. What we did is we took out the filters from these particular sensors and put in 800 nanometer filter in some instance and 900 nanometer filters. And we got the radiation that is emitted from the flames at these 2 wavelengths. And using the equations shown before, we could get the instantaneous planar temperatures and soot volume fractions. And we validated the soot temperature correlations again with literature values. So this shows some of the results from the underfire region. Here it shows typically on the left hand side you see the soot volume fraction in parts per million. You can see that in the middle of the flame, since we are about 100 millimeters above, the maximum soot is available right in the middle of the flame. If you are way down close to the burner exit, you will see more like a ring. I'll show you some data like that later. More like a ring where the inner part is cold and less soot, and the outer part has the flame sheet. Similarly, the temperature is the peak at the middle, since we are quite high up in that particular flame. And just below that, you see the validation. In the literature, what you have is only two lines where it is, since the scatter on the data is very high, it just I have plotted the +1 sigma and -1 sigma to their data, that shows by the red line and the green line. And generally, we find very good correlation between soot volume fraction and temperature. And the only place where the correlation is not that great is at the lowest flow rate, and that has something to do with the intermittency problem, with the flame not being there quite at all the times. Similarly, for the propylene air, also we have got very good correlation between the soot volume fractions and temperatures. So this was our second experiment, and we saw that we can very clearly get temperatures and soot volume fractions in these sort of hydrocarbon flames. If you use something like an AL, like a monopropellant, you can use Al2O3, aluminum oxide particles, to get the particulate volume fraction and temperatures. Now, just to show that we are also capable of getting transient results, we can get transient data at 1000 Hertz currently with the sensors that we used. Here it shows the time along the scale and the distance, and this shows the temperature profile. So you can see, since it's a turbulent flame and it is from a 50 millimeter diameter burner, you have very predominant frequencies that go up and down, up and down, up and down, with a specific pulsation frequency. Similarly, for the soot volume fraction, you have very similar behavior. The soot volume fraction ranges from about 1 ppm to about 10 ppm, which is roughly what is also found using intrusive probes within these flames. The next one that we did was a hydrogen air flame. We used a turbulent hydrogen flame from a 10 millimeter diameter burner that you see here. So this is a turbulent flame, and we measured the emission at 310 nanometers using OH filters in front of the receiver arrays. These measurements were done 25 millimeters above the burner exit. And here it shows you, initially it just shows you the raw voltages as a function of distance, that we see that the voltages are about 1 to 1.2 millivolt. So it is the voltages are quite low, since the flame is also quite small, which comes from a 10 millimeter tube. And on the right hand side, you see the OH intensities. One thing is we get very good convergence between the measured and deconvoluted intensities. I have not shown that particular plot here. We do note that there's a small asymmetry in the reactions zone, and the values that we got were very consistent with literature values of Zhou et al. That was published in 2018. To get the absolute concentrations of OH, what we did is we assumed temperature profiles provided by Zhou et al. Then I'd like to close up with some previous data. That is what we got from a water spray and a nozzle. So here you can see the small nozzle is actually a fuel nozzle that is spraying downward. And we measured scattering and extinction using a 2D array. This was a 2D array which had 2 into 512 elements. The laser wavelength we kept at 632 nanometers, and we used the Meade theory to obtain both drop sizes and surface area densities. I had shown that formulas previously. So this is some of the results that you obtained. First, it shows the scattering intensity. I have not shown the extinction because it has been published quite a lot in lots of different places. So this is the scattering intensity. And from the scattering intensity, what we get is the plot shown on the far right as a function of distance, the x distance and y distance. It shows you the solder mean diameter. You can see the solder mean diameter is higher at the boundary of the spray, and that is typical of sprays. And here we have the surface area which is shown in the middle. We did compare our data with PDA measurements. So the PDA measurements is shown as this red spot, and this is the extinction scattering tomography system. It is quite close to each other. Only on the left-hand side there is some asymmetry. It could be that since the PDA is measuring across only one profile like this way, while this one is showing the whole thing, maybe if you had measured like this way, it would have shown higher on both sides. So it's very difficult to compare it unless we have the full contour. Right now we have only one particular axis along this way, and you can see here it is lower and here it is higher, while PDA actually showed. We are not very sure whether the nozzle is aligned exactly the same in both measurements. So now I'll just move on to my conclusions. The conclusions are we are able to get the planar soot volume fractions were estimated with very good agreement with values reported in literature. The temperature and soot volume fractions were consistent with past measurements. To get, if we have further data, maybe we can get better agreement. The main reason is there's not that much data out for planar soot volume fractions and temperatures in these sort of flames. OH estimates are in qualitative agreement, because quantitative agreements we ended up using the temperatures that were published in the same paper. And if we had used two wavelengths, maybe we could have got the temperatures also simultaneously. The estimated drop size measurements were confirmed with PDA measurements, and finally we can say that we have completely validated the sensor suit, and it provides a useful diagnostic to study turbulent flames. So now I'd like to open it up for questions. If anyone has any questions, then thank you very much for listening to this presentation.